gentlemen, welcome to optimization. What, you may ask, is optimization? Optimization is trying to maximize or minimize something. But it's a real something, not just a point on a graph. For instance, hi, Addie. For instance, one of my uncles worked at a place in Fort Smith for a long time, and what they did was they built cardboard boxes. How many things do you get in the mail that come in a box, in a cardboard box? Well, everything. Okay, Amazon ships in cardboard boxes, right? All kinds of places will ship in a cardboard box. Bad memories, when I worked at the chicken plant in the summers when I was in college. Really makes you want to go to college, believe me. I worked in the freezer, and we packed chicken in boxes, okay? Well, somebody's got to make those boxes, right? Well, let's say that I go to this box place and I say, I need boxes that will hold this many cubic feet of chicken. Cubic feet of chickens. Frozen parts of chickens. But I need you to minimize the amount of cardboard that you use because I want to pay as little as I have to for these boxes. So trying to minimize the amount of cardboard used to build a box would be called an optimization problem. That kind of makes sense? You're going to, you want to design a new soda can, right? You're trying to decide, I need it to hold this many, cubic milliliters or ounces? Cubic milliliters, that's dumb. I need it to hold this many milliliters or this many ounces, but I want to minimize the amount of aluminum that I use to make the can. So, do I make it taller? Do I make it wider? Do I make the height bigger or do I make the radius bigger? How do I minimize the amount of aluminum that I use to make that can? That's an optimization. Now, optimization can be maximizing, okay?
So is that like you those metrics like the 2 graphs and the X cross? That point is like the best thing to do or whatever?
What you're talking about, I think, is like where you would make a profit. So if you graph your cost and you graph your revenue, where they cross, where they intersect, is where the money that you are bringing in is equal to the money that you're having to pay out. After that is your profit.
So could you do like soda can thing where like you put one graph of the size or whatever the soda can or how much it holds and one graph of like.
Well, remember how much it holds would be constant. If I'm telling you I need it to hold this many ounces, that would be a constant. Okay? So let's just dig in. So maximizing would be you got this many square feet of cardboard. That's all you got. How can you make the box that will maximize the volume? Great, that's an excellent example. Okay, so Sparks has 5 rules or 5 steps in his general approach to solving optimization problems. So here we go. Oh, let me back up. The word optimization comes from the word optimum or optimal. Have you ever heard that? What is the optimal? Huh?
Oh, yeah. Transformers. Come on.
Optimal or optimum is kind of like the best.
So, yeah, that's it.
Okay, all right. So here we go. That's a D. Determine. You know what? It would be easier for me and faster for all of us if I just put these under the doc cam. Avery, when you watch this video, the things that go in these first 5 boxes, your classmates are being really snarky. Just look at the filled in notes and you can write these 5 things down. A manufacturer wants to design an open box having a square base and a surface area of 108 square inches. We want to maximize the volume. What is the maximum volume? So the questions are, what dimensions will produce a box with maximum volume, and what is the maximum volume? Now, if you go back to your steps, look at number 1. What is the quantity that is to be maximized or minimized? So I want you to write maximize volume. That's the first thing I want you to write down, because you can get so lost in the math that you forget where you were going. Step 2, draw a picture, define a variable, or use some formula to identify the quantities not valued. I can draw a box. We're trying to design an open box that has a square base. I can do that. You can do that. When you were a kid, you got so excited when you learned how to draw like a box like this? Remember? Let's see here. Missed one. Now it's open, so it would look like that. Now, this box has a square base. How would I indicate square base?
The line. Right.
Like the triangle or right?
What? Oh, no. Let's do this.
I guess.
Yeah. Now, this thing may or may not be a cube. I don't know how tall it is, so you cannot assume it's a cube. So you need to let your height be something else. H, you could let it be H, you could let it be Y, you could let it be H, it doesn't matter. Now, what else we got? We drew a picture. Oh, we know the surface area, don't we? Okay. Let me do this first. We want to maximize the volume. What is the formula for the volume? X times y, so x squared y. Now notice, over here on the right side of the equation, we've got 2 variables. When you have more than one variable, look down at number 4. If the primary equation, and this is the primary equation because this has the variable that we are trying to maximize. When that equation has more than one variable, a second equation will need to be written. We can write the second equation because we know this. So what we're going to go do is we're going to write an equation for surface area. Now, what is an equation or formula for surface area? How do you find it? We'll pick up there. Now, so we had an equation for volume, which we wanted to maximize, but it's got 2 variables in it, x and y. And according to Sparks, if you have 2 variables in your equation, then you have to go write a secondary equation. And we'll go through this. So we said at the very end of class before lunch that the surface area of an open box with a square base is x squared plus 4xy, correct? Now we know what the surface area is. The surface area is 108. That is the surface area of an open box with a square base. The area of the base is x times x squared. The area of one face is x times y, and you have 4 of those. Correct, open box. Now, you say, okay, so fine, what does that secondary equation do for me? What I need to do, I'm going to solve this for either x or y, and then I'll substitute back into my volume, so I'm going to have volume equals, and all I'll have is one variable over there, so it's easy to take the derivative of.
Can't you just plug into the the surface area one and find what y is?
Say that again, please.
Because like if you solve for x in terms of y, and plug that down and find, I mean, could you substitute the value of x back into?
I don't know what x is.
Well, like
Just, here we go. Here we go. If I'm going to take this equation right here, and I'm going to solve it for either x or y. Now, one of those, I hope is obvious to you that it's easier to solve for. If I want to try to solve this for x, that's going to be a real pain in the neck, and in fact, you can't do it. Well, if you subtract 4xy from both sides and then try to take a square root, you still got x on both sides. So you haven't solved for x. The solving for y here is going to be real easy. So what I'm going to do is I'm going to subtract the x squared, and we've got 5 problems to do, so we're going to have to hoof it. I'm going to have 108 minus x squared equals 4xy. And then I'm going to divide both sides by 4x. So I know what y is. Y is 108 minus x squared over 4x. Now, do you see where that came from? Now, here's the thing. This relationship between x and y came from the surface area. So that relationship between x and y will also hold true for the volume because it came from the same box. So what I'm going to do is I'm going to substitute this in for this y, and now I have an equation for v that only has x in it. Okay? So v equals xy. Now I'm going to clean that up just a little bit, because I'm going to take the derivative of this. Because why am I going to take a derivative? Because I want to maximize volume. In order to maximize something, let's remember, I take the derivative, I find my critical numbers. When I'm trying to find a maximum, and okay, and I'm not going to be dealing with endpoints. I'm not worried about endpoints because x cannot be 0, right? And there's no other endpoint. I don't know how big. But what I'm going to do, if I want to maximize the volume, I'm going to take the derivative, find my critical numbers, and do what? I'm going to figure out, I'm going to set them equal to 0. I'm going to find my critical numbers, and I'm going to put them on a sign chart.
Let's see what's negative, positive.
So what am I looking for to maximize? When the volume changes from increasing to decreasing, which means the derivative changes from, that's what I'm looking for. I want to find the critical numbers of my volume, put them on a number line, and I want to see when does my derivative change from positive to negative, because that means my volume would change from increasing to decreasing, where I'd have a maximum. Okay? So what I've got to do is I've got to take the derivative of this. I could do it right now, but I would have to do the product rule and the quotient rule, and I don't want to do that. So what I'm going to do is I'm going to see if I can just clean that up using algebra to make it a little bit easier to mess with. Okay? Well, I could cancel that x with one of those. Oh, can I do that? Well, I did. Yeah, there you go. Just watch me. Yeah. Now, what I'm going to do, I may change my mind. Okay? That's one of the things about working problems. I may decide, no, I don't like that way, and I may erase it. Okay? You will go through your life in calculus or farther on, whatever. You're going to have a mechanical pencil in one hand and an eraser in the other.
So could you get rid of like the 108 4 by just separating it, and then that 108 over 4 just becomes a...
So what I'm going to have That's going to be 108x minus x cubed. 108, I don't know where the 8 went. 108x minus x cubed over 4. Yes? Isn't that a yes? Now, I need you to understand, there are different things I could do. I could do what Mason said. I could split this up into 2 fractions. Now, 108 over 4 is 27. 27. Okay. So that's 27x minus 1/4 of x cubed. By golly, I can take the derivative of that. That's easy. Now listen, I'm going to write this as v of t over here, okay? Not t, x. So now we're going to take the derivative. V prime of x is 27 minus, okay? Find your critical numbers. If I add 3/4 x squared to both sides, yes? Multiply by x squared equals 36. Good. 3 goes into 27 9 times. 9 times 4 is 36. I am just immediately going to toss the negative because length cannot be negative. Now, that is my only critical number. Now, I know what many of you are going to start thinking as we go through more of these problems. You're going to think, well, that's the only critical number, so that's the answer. By golly, you're going to put it on a number line, and you're going to make dang sure that that's a maximum. And if you don't, I'm going to count something wrong. You don't even mess with me. Now, remember, this has to start at 0, right? You can do 1 and 10. You can do 1 and I don't care as long as it's bigger than 6. Bless you, bless you, bless you. Plug them back in here. Because we want to know, is the derivative positive or negative? Question.
Well, they work that. I have a question.
Okay, when x is 1, is this positive or negative? When x is 10. So we know that x equals 6 gives us a maximum. Okay there? Now let's go back. Way back. What dimensions will produce a box with maximum volume? Okay, come on. What's x?
6. 108 divided by 36.
Aha! Now look here. Look here. What is the y value?
3.
So 108 minus 36 divided by 24, whatever that is. 3. So 6 and 3. I'm going to erase just because I'm tired of scrolling back and forth. But we're going to answer the questions. Okay. 6 inch by, is it inch? Yeah. By 6 inch by 3 inch will produce a maximum volume. And then it asks what is the maximum volume of cubic inches. Coincidence. Coincidence. Pure coincidence.
Yeah.
I cry. A box is to be built from a rectangular piece of cardboard that is 25 centimeters wide and 40 centimeters long by cutting out a square from each corner and then bending up the sides. Can you visualize that? Find the size of the corner square that will produce a container that will hold the most amount of soup. This is called soup in a box. Don't ask me. I didn't write the problem. Oh, sweetheart, I don't have a clue. Whoops, what is that? Okay, right picture. We're going to cut out a square. I have a rectangular piece of cardboard. And I'm going to cut a square out of each corner. Now keep in mind what's going to happen is I think we're just building our bowl because there's not a top. So I think we're just building a bowl. A square rectangular bowl. Yeah, it says cardboard. Maybe they're going to line it with something. Don't ask. I didn't write the problem. Holler at Sparks. There you go. Oh, that's it. Now, find the size of the corner square. I want to find this. I want to find these dimensions, x and x. Now, once we fold up those sides, look at the box we're going to have. Aha. Yeah, no soup for you if you've watched Friends, or excuse me, Seinfeld. No soup for you. Let's see here. Okay.
Do we gotta draw that?
I certainly would draw that. Now, so you got your box, right? Bless you, dang. What's this height right here? X. What's this length right here? 40 minus 2x.
25 minus.
Yep. Right there is 25 minus 2x. Yes, we have cut out those corners and then folded it up. I want to produce a container that will hold the most amount of soup. What am I trying to maximize? Volume, soup. The volume, the amount of soup, volume. Question?
Wouldn't, like, no matter which way you cut it, it's the same size box, but just hold the same?
No. It's a great question. No, the volume will be different depending on how big the square is you cut out of the corner. Promise. It will be different.
What if you want, like, the smallest possible then? Because that would,
Not necessarily.
I believe the numbers.
Not necessarily. I can show you some stuff about that, but the answer is no. Because you could make it 1/4 of an inch high. You could make it 1/8 of an inch high. And I guarantee you that ain't going to hold much soup. That's right. But I promise, the volume does change. Now, we are wanting, what I didn't write down at first, we are wanting to maximize volume, but I put an L right there. There we go. What is the volume of that box? Aha. The volume of that box do you have to multiply it out? The answer is no, but I'm going to. But I'm going to explain why. Do we need a secondary equation is the first question. Because we only have one variable over here, so I do not need a secondary equation. So I'm going to take the derivative of this. If I leave it alone, I'm going to have to do the product rule a lot. Okay, so if we did 40, that I don't even know what that is, 40x minus 2x squared times 25 minus 2x, then we absolutely can do the product rule. And a lot of you would choose to do that right there. Okay? But my druthers is I'm just going to multiply the whole darn thing out. But if you want to do product rule right here, you absolutely can. I doubt it. I doubt it. So, yeah, but fiddle. What's 4 times 25? 100. So 40 times 25 is 1,000. Minus 80x squared minus 50x squared. Is that right? Yes. Plus 4x cubed. So that's 1,000x minus 130x squared plus 4. You know what? Could I take out an x? Sure, but that puts me right back to doing product rule. V prime. Now here's the deal. I might not have made the best choice because if you did product rule, it might be easier to find your zeros. But I'm going to go with what I got. 4 will go into all those. Will anything bigger than 4? 12? No. Yeah, 4. 3x squared minus 65x plus 250. The answer is you may get a calculator on this problem. Okay. If I was working this problem, I'm pretty sure we'd have a calculator, and I probably would have stopped right there, thrown it onto my calculator, and looked for what? Zeros. Because I'm with the derivative. Throw it on your calculator and find the zeros. You cannot. If this is a free response problem and you don't show the derivative, you will get 0 points. I'm just telling you. Okay. You do not want to leave easy points on the table. What? What the? Oh, God bless Fresh. So this equals 0 when x is equal to 5. Okay, 5. Now remember, we're trying to maximize volume, so what do I have to verify about that x equal 5? Dadgum. I better
Wait, what about 16?
Okay, let's talk about that. I'm hearing that there's a second x value. If you get 16, is that possible? If you cut a square that's 16 long on that means 16 long there. So yeah, and that's great. I'm glad you mentioned it.
Then again, they're putting bigger box.
Well, they put wine in boxes, right? So let's try 1 and let's try 10. If x is 1, if x is 1, that's positive. If x is 10, that's negative.
So maximum.
Yep. There was one other zero, 16 and something. Is that correct? Yeah, I wouldn't call it extraneous. It wasn't even in the domain to begin with. Because if you think about your domain really, what's the biggest x, the biggest length you could cut out of this side?
12.5.
If you cut out 12 and a half, you don't even have a box, right?
So like,
So your domain here would be, right? So 16 is not even in that domain. You know what? I would not worry about it. What I would do is I would take my answers that I get on my graph and I'd go up there and check them. And I'd say, oh, that 16 is not possible. That's all I would do. All right, so we got x equal 5. Okay, so what does this say? Find the size of the corner square that will produce a container that will hold the most amount of soup. What's the size of the corner square? 5 by 5 what? Okay, so you're going to say a 5 centimeter by 5 centimeter corner square will produce, and I'm reading from the problem, will produce a container that will hold the maximum amount of soup. Does it ask you for the maximum does it ask you for the maximum amount? No. Don't tell them if it doesn't ask, just in case you might make a mistake.
oh, because if you have a wrong answer on the
Questions? Number 3. Oops. Here we go. Have you ever noticed that you have some books that are, you know, sort of 8 by 10-ish, and then you have some books that are little, and then those coffee table books,
they're huge.
okay? Let's look at this. A rectangular page is to contain 24 square inches of print. The margins at the top and bottom of the page are to be 1.5 inches, and the margins on the left and right are to be 1 inch. What should the dimensions of the page be so that the least amount of paper is used?
Oh, that makes sense.
It does. I know, it's pretty good, huh? Okay. What am I trying to optimize? Read the whole thing. Read the last sentence. What should the dimensions of the page be? So I'm looking for,
Parameter.
I'm trying to minimize area. So I'm trying to minimize the area of the page. And I'm going to write this, the whole page. That's what I'm trying to minimize. Now here's what we know. We know that this area right here, and I'm going to do that in yellow so that I can write over it. I know that this area right here is how much? 24 square inches. I know that the margins at the top and the bottom are 1.5 inches. There's 1.5 inches, and there's 1.5 inches. I know the margins on the left and the right are 1 inch. Are we okay so far? Now, I've got to assign a variable. I do not know that this is a square. I know it's a rectangle, but I don't know if it's a square, so the dimensions cannot be the same. Now, I can do one of two things. I could let the entire this be x, or I could let this be x, okay? And the question is, well, how do you know which one? The answer is it doesn't matter. I'm going to just choose, I'm just going to arbitrarily pick, let me see here. I think I'm going to just let this whole thing here be x. Now here's what I need you to understand. I'm trying to work these problems without notes so that you can try to see my thought process, that if I think, dang, I screwed up, and I'll just erase and do it different, okay? If I realize that what I've done is not so helpful, I'm going to go back and I'm going to make this length x and this length y. You see what I'm saying? Okay? What do you know?
Wouldn't it be, so then the equation would be y minus 3 times x minus 2.
Yes. Yes. Now, the area that I'm trying to maximize, write an equation for the area I am trying to maximize. Minimize. Minimize. What am I trying to minimize? No, read. Whole page. I'm trying to minimize x times y. I have two variables. I need a secondary equation, and that's the one that Abby just said. Can you get it? I know this. I know that x minus 2 times y minus 3 is equal to what? 24? I'm beginning. I'm beginning to think that I maybe need to change it and do it the other way. But let's look. Let's FOIL this out. Don't FOIL it out. Don't write any more in your paper. Let's FOIL this out. The xy this isn't going to work. How would I solve that for? Well, no, wait a minute. No, wait a minute. No. No, I can make this work. I can make this work. Do you want to solve it for x or do you want to solve it for y? Well, fine then. Okay, let's solve it for x. How am I going to do that? Oh, wait. Oh, wait. Oh, wait. Maggie said, what did Maggie say? What did Maggie say?
Divide it by a term. Yeah.
Maggie said right here, divide both sides by y minus 3. And then we'll add 2 to that. X equals, well, I don't do math cards. What should we do? Extra credit point?
Yes. Yeah, she should get
Oh, that's a little steep there, kiddo. That's a little steep. I was thinking 1. Now look, that's what x is. That's what x is, right? So I can take that and I can substitute that right back in here for x. And then the only variable I'll have is y. Indeed. Indeed. So the area that I'm trying to minimize is x, which is this, times y. So I'm just going to put y times now I have to take the derivative of that. Do I want to leave it that way, or do I want to distribute the y? You tell me distribute the y, so let's distribute. Let's see what happens. This is 24y over y minus 3 plus 2y. You could. I'm not, and I'm going to tell you why. It's real easy to take the derivative of 2y, right? And if I get a common denominator, then my numerator is going to be quite a bit more complicated. Derivative. Now listen, here's the deal. If you have a calculator, you can put that in y1 and have y2 as your derivative, right? But you're going to just practice here. Derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared. Over the top times the bottom minus the derivative of the bottom times the top over the bottom squared, and then plus 2. Oh, but look at that. Look at that numerator. Look at that numerator. A prime equals, what's that, negative 72? Negative 72 over y plus 3, quantity squared, minus 3 squared. Sorry? I distributed. I distributed right here. 24y minus 24y is 0. And there's your negative 72. No. Because that y minus 3 is only multiplied by that 24 and not by this. It has to be a common term to the whole thing. What do you want the derivative equal to? 0. So it may be faster for you to do that in your calculator or to do it by hand. I don't know. I'll try it by hand. If you want to try it in your calculator, knock yourself out, and let's see if we get the same answer. Oh, let's do this. Does y equal 9? You'll get a negative as well, but you'll get a negative number as well, but that's not going to be in your domain because we are dealing with lengths. So you go into your sign chart. There's 0, 9, 1 and 10. Yep. What about what 3? That is a very good question, so let's discuss it. Yeah, if you'd have solved it a different way, but still, if you'd solved it a different way, you'd have a different number in your denominator. But for y, yeah, y can't equal 3 either. So let's see what happens if we put 3 on there. So I got to pick another number, eh? 5. I think I know the answer to your question, but I'm going to let the sign chart do it because I'm not 100% sure. If y is 1, here's the derivative, right? If y is 1, then this is going to be a negative divided by a positive. So it's going to be negative 72 divided by 4 plus 2. That's negative. 5. 5 minus 3. 2 squared is 4. That's still going to be negative. And 10. 10 will be 49. Is negative 72 divided by 49? There you go. So it's going to be positive. And remember, we were trying to do what? Minimize. Negative to positive happens at 9. It's a good catch, Mary Grace. So negative to positive happens at 9. So what is 3 in this case? It's just nothing very interesting. You know, it's not, well, yeah, it might be a flat spot maybe. Yeah, but it's nothing interesting. Okay, so y equals 9. What are we trying to do? The dimensions of the whole page. Okay, so y is 9. Oh, I can put it right here, couldn't I? Y is 9. 24 divided by 6 plus 2, 6. So this is going to be a 9 by 6. So you're going to say 9 inches by 6 inches are the dimensions of the page, so the least amount of paper is used. Or you could say a 9 by 6, 9 inch by 6 inch will minimize the amount of paper. Huh?
This does not feel very related to like what we were doing before.
But I guarantee you it pulls in everything you've learned, right? All right, next. I'm trying to decide, all right, I don't know,
8 minutes.
one of these may have to be, all right, a rectangle is bounded by the x and y axes, and the graph of y equals 3 minus 1/2 x. This line is y equals 3 minus 1/2 x. What length and width should the rectangle have so that its area is at a maximum? I'm sorry? You can't, yeah, no. It wouldn't be a multiple choice.
Yeah, we know our x is 3, y is
Oh, gosh. I am trying to maximize. You guys are just trying to figure out.
The easiest cheap shot way.
Not easy, lazy. Yeah, cheap shot, somebody said. We want to maximize the area of the rectangle. What's an equation for the area of that rectangle? X times Y. Well, I need a secondary equation because I have two variables. Okay, guess what? I've already got
Just
one.
use it, yeah.
I've already got one. My secondary equation's sitting right here.
Yeah, why does that even
Because that line goes through one corner of that box.
That's the point.
Yep. So area equals X times 3 minus 1 half X. 3X minus 1 half X squared. So a prime of X, and notice I put X in now because that's my only variable. Well, daggum. Is that one that easy? What's X? Oh.
Then divide by negative.
You subtract 3.
If X is 3, 1, 5. Would you stop? Would you stop? All right, derivative. If X is 1, if X is 5, what is X equal 3? X equal 3 is going to give you a max. Wait, what? Okay. That was the easiest problem we've done, isn't it? So, well, you betcha. What length and width should the rectangle have so that the area is at its maximum? Ah! Sorry, Avery. Oh, yeah, I'm fine. Scare myself. The area is at its max when the dimensions are. Now, do we have a unit? The area is at its max. That, I think that implies
Or it's at the max.
it is at, how about this? The area is at a max. Okay. The area is at a max. No, that's, well, I appreciate that. When, okay, so when the dimensions are what? 3 by. Now, we got to be careful. What's it asking? It says the length and the width. So we better restate that, eh? When the length is 3 and the width is 3 halves. Determine the point on, okay, let's just look at this just really, really fast. Determine the point on this line so that the distance between the line and the point 1, 2 is at a minimum. Put that, oh, I'm sorry, never mind. My bad, I started to say put that phone away and I realized that Tate has a calculator. Well, he was chuckling. I'm just laughing to himself and I thought, have you got your phone hidden behind that calculator? Okay, just check. I had a student do that once. That's what I'm trying to minimize, correct? That little purple piece. But remember, I can minimize distance as long as those two pieces are perpendicular to each other, right? So if you're going to call this point right here, the point that's on the line is going to be xy. And what you're going to do is you're going to use the distance formula. Distance formula. And this will be your secondary equation, okay? You can walk yourself through that with Sparks' notes.